Okay, so now we begin chapter 2, which is on sequences and series. And today in this video, we are going to start talking about sequences. Specifically, we'll talk about the definition of what it means for a sequence to converge, uh, what is the limit of a sequence, and what are some consequences of this definition. Okay, so that's our goal for today. So we have talked about sequences before, but since we are beginning an entire chapter, let me just formally define what a sequence is. A sequence is essentially a function from the natural numbers to R. So in particular, a real sequence is this, a real sequence. So implicitly, we'll be talking about real sequences unless I explicitly mention otherwise. So a real sequence, xn, we are going to denote it like this, is a function from the natural numbers to R, right? So which means the sequence takes a particular value for every natural number, 1, 2, 3, 4, and so on. So as an example, suppose I say that xn is equal to 1 by n square. That defines a sequence because corresponding to the natural number n, the sequence takes the value 1 by n square. Okay, so that's the definition of a sequence itself. Next, we are going to get into what it means for a sequence to converge. Okay, so I won't keep saying real sequence. Implicitly, every sequence is going to be real in this course unless otherwise specified, right? So a sequence xn is set to converge if there exists a real number x such that the following condition is true. For all epsilon greater than 0, there exists a number n naught such that the absolute value between xn and x, the entries of the sequence and this real number x, is less than epsilon for all n greater than or equal to n naught. Okay, so here is your definition of what it means for a sequence to converge. Okay, so it converges in words if there exists a real number such that the elements of the sequence get progressively and arbitrarily closer to x as n becomes large, right? That is what in words it means for a sequence to converge. How do I formalize this? A sequence is said to converge if there exists a real number x that satisfies the property that for any positive epsilon, think of epsilon as an error threshold, okay? For every positive epsilon, there exists an n naught such that the entries of the sequence beyond n naught are within an epsilon of x. That is, absolute value of xn minus x is less than epsilon for all n greater than or equal to n naught. So n naught is your threshold beyond which every entry of the sequence is within the interval x plus epsilon and x minus epsilon. Okay, and the important thing here is that epsilon can be any arbitrary positive number. You can take epsilon to be 0.1, 0.01, 10 raised to minus 25, whatever you like. No matter how small an error threshold you have, there exists a far enough point n naught such that beyond n naught, the entries of the sequence are within epsilon of x. Okay, if this is true, then indeed you should be able to convince yourself that the entries of the sequence do get progressively and arbitrarily closer and closer to x as n becomes large, which is when we say that the sequence converges. Okay, so in this definition, remember, to be able to show that a sequence converges, you have to come up with a real number x such that the sequence satisfies this property. Okay, so implicit in this definition is the suggestion of this number x. Okay, that this number x has a name. This number x is what is called the limit of the sequence. Right, and typically we will write either limit n tends to infinity xn is equal to x, or simply we say xn right arrow x, right? Both of these things mean the same thing. So when I say something like this, say xn, so this is sometimes read as xn tends to x. Okay, so when I say xn tends to x, where x is some real number, let's say 1 or 2 or 10 or whatever, I'm essentially saying two things. Firstly, I'm telling you that the sequence converges, and I'm also telling you what the limit is. The limit in this case is x. Okay, so when I say xn tends to x, where x is a real number, I'm saying that the sequence converges, and I'm identifying explicitly what the limit is for you. Okay. Finally, on the same lines, a sequence that does not converge is said to diverge. Okay, so convergent sequences satisfy the property that there exists a real number such that the entries of the sequence get arbitrarily close to that real number as n becomes large. That's the first definition. And a sequence that does not converge, in other words, that does not a sequence such that there does not exist a real number with this property holding, such a sequence is said to diverge, or such sequences are called divergent sequences. Okay, so let's begin with a very quick example. Let's use the same example that I used before, which is that xn is equal to 1 by n square. Okay, in this case I'm going to claim that the limit is 0. In other words, I'm going to claim that xn tends to 0. Now, how would I prove this claim? The way I would prove, so again, this is important to understand that later we will look at ways of shall we say being able to argue convergence of a sequence without explicitly identifying the limit. But at this point, by the definition that I have written for convergence here, to show convergence of a sequence, you have to identify the limit. You have to identify the x. So in this case, I'm claiming that x is 0. Now, how do I show that xn tends to 0? Well, what you do is look at, for any epsilon greater than 0, look at the difference between xn and 0. In this case, this difference is exactly 1 by n square. And this is of course less than epsilon if and only if n is greater than 1 by square root epsilon. Right? So I can just take n naught to be something larger than 1 by square root epsilon. Say 1 plus the ceiling of 1 by square root epsilon. Right? If I do this, you can convince yourself that in fact for all n, then if you look at xn minus 0, this thing is indeed less than epsilon for all n greater than equal to n naught. Okay, and once I've said this, by definition, I have proved that xn in fact tends to 0. Okay, let us next do a fairly trivial example of a sequence that does not converge. Suppose I take xn to be, well, minus 1 raised to n. In other words, the entries of this sequence essentially alternate between plus 1 and minus 1. Okay, so how do I prove that this sequence diverges? I want to prove that this sequence diverges. So I'm going to let you fill in the details for this, but think about how it is that one would go about doing this based on the definition that we have. What you have to basically show is that there does not exist any real number x such that the condition is satisfied. So there does not exist any real number x such that for all epsilon greater than 0, there exists an n naught such that this condition is true. right? So you have to show that such an x does not exist, right? So yeah, if you're doing this for the first time, try and think about, so I'm going to leave the details as an exercise to you. Try and think about how a formal argument to this effect can be made, right? Intuitively, you're going to exploit the fact that if epsilon is small enough, if the entries of the sequence being close enough to +1 implies that they cannot be close enough to -1, and vice versa. If the entries of the sequence are close enough to -1, then they couldn't possibly be close to +1. So that's kind of the intuition that one has to exploit to show that such an x does not exist. Okay, so that's therefore an example of a divergent sequence. Let's do one more example. In this example, I'm going to take xn to be, let's say, 3n plus 1 upon 7n minus 4. Okay, again, I have to basically come up with a claimed limit and show that it is in fact the limit, right? So in this case, my claim is going to be that xn tends to 3 by 7. Okay, so my claimed limit is 3 by 7. How do I go about showing this? Again, for some positive epsilon greater than 0, I basically look at the error between xn and x, right? In this case, that would be 3n plus 1 upon 7n minus 4 minus 3 by 7. So one level of algebra here will show you that this is in fact 19 upon 7 times 7n minus 4, right? And this quantity is less than epsilon. Again, invert this and check that this is in fact equivalent to saying that n should be greater than 1 by 7 times 4 plus 19 by 7 epsilon. Okay, that level of algebra I'm going to leave to you. And so what this tells me therefore is that I can just set n naught to be some natural number that is larger than this. So as before, I can just take the ceiling of 1 by 7 times 4 plus 19 by 7 epsilon, let's say plus 1. And in this case, again, it follows from our calculations that for whatever epsilon you choose, if n naught is chosen in this manner, then indeed xn minus, well, in this case 3 by 7 is in fact going to be less than epsilon for all n greater than or equal to n naught, right? This shows that in fact 3 by 7 is in fact the correct limit, and the sequence advertised here is in fact convergent. Okay, so this is just playing with the definition of convergence of a sequence, and yeah, doing a few examples. One example where the sequence doesn't converge, and the others where it does. Okay, so now let's look at one result on how limits can be combined. Limits of different sequences can be combined. Again, this is going to be a very trivial, a very straightforward consequence of the definition of convergence in the first place. Okay, so suppose that I have a sequence xn that converges to x, and another sequence, let's say yn, that converges to y, then in fact the following hold. Okay, if you look at the sequence xn plus yn, now this is indeed a sequence, right? So when I say xn plus yn, this is a new sequence whose nth entry is the sum of the nth entries of the first sequence and the second, right? This sequence also converges with the limit of x plus y. Okay, so if I add two sequences, the limit becomes the sum of the two limits. The second property here is that if I multiply two sequences, so x and yn is a sequence whose nth entry is the product of the nth entries of x and y, right? Of the first and the second sequence. This thing has a limit of xy. Multiplying sequences results in the limits getting multiplied as well. The third part is that if you multiply any sequence with a constant c, so c is just, think of it as a scalar. So c times xn tends to c times x. Similarly, c plus xn tends to c plus x. Okay, and the fourth part is that if the limit x of the first sequence xn is not 0, then in fact the reciprocal sequence, right? The sequence where every entry is the reciprocal of the original sequence will in fact tend to 1 by x. Okay, so these are all, as we will see, fairly elementary properties of the definition itself. So let me go through the proof. Parts of the proof I'm going to leave as an exercise to you, but some of these things are easy, but these are techniques that you have to get used to when you're playing around with limits, right? So how do I, for example, show that xn plus yn converges to x plus y? Okay, so again, as always, the goal in this particular case, the limit has been suggested to you, so you just have to prove that this is the correct limit, right? So the goal of identifying the limit has been shall we say taken away from us, because I just have to show that the advertised limit in the statement of the theorem holds. Okay, so now for epsilon greater than 0, I'm going to use the I'm going to look at basically the difference between xn plus yn and x plus y. This is of course the sum of the differences between xn and x and yn and y, right? I can then use the triangle inequality to show that this mod of a plus b is less than or equal to mod a plus mod b, right? Right, so now all I'm going to use is the fact that if I want to make this overall difference to be less than epsilon, it suffices if I make each of these pieces to be less than epsilon by 2, right? And indeed, after a certain point of the sequence, each of these pieces will in fact be less than epsilon by 2, given that xn converges to x and yn converges to y, given the hypothesis of the problem, right? So since xn converges to x, there exists some real number, let's call it some natural number, say n1, such that mod of xn minus x is less than epsilon by 2 for all n greater than or equal to n1, right? Similarly, since yn tends to y, there exists n2 such that absolute value of yn minus y is less than epsilon by 2 for all n greater than or equal to n2. Okay, now what I'm going to do is set n0 to be the larger of these two numbers, which is the max of, let's say, n1 and n2. Okay, so which means for all n greater than or equal to n0, because it is the larger of these two numbers, both of these properties hold. This holds as well as this holds. So therefore, for n greater than or equal to n0, the absolute difference between xn plus yn minus x plus y, right? First I'm just going to reproduce the old inequality. This is a triangle inequality, which is xn minus x plus yn minus y. And now each of these is in fact less than epsilon by 2. And so the overall thing is less than epsilon. Okay, so this shows that in fact for whatever epsilon you give me, the difference between xn plus yn and x plus y will become smaller than epsilon for n greater than or equal to n naught, which basically proves to you that xn plus yn tends to x plus y. Now, this was the proof of part A. The proof of part C I leave as an exercise to you. Namely, if I spelled this wrong, E-X-E-R-C-I-S-C. Yeah, so this is a trivial statement that if you add a scalar to a sequence, the limit is going to be the sum of the scalar plus the limit. If you multiply a sequence with a scalar, the limit is going to be simply the same scalar multiplied by the original limit. Okay, so C is an exercise to you. What I'm going to do is quickly show you how I can leverage A and C to prove B. Okay, so what is B? B, remember, is I wanted to prove that x and yn tends to xy. Okay, now how do we go about doing this? Again, there are many ways of going about this argument. Essentially what you have to do is break down the error between xn, yn and xy into pieces, each of which you can argue becomes small enough, right? That's the idea. So one, shall we say, cute way of doing this is to say that xn, yn can in fact be written as follows. Can be written as xy plus xn minus x times yn minus y plus x into yn minus y plus y into xn minus x. Okay, I leave it to you. Just open up the right hand side and convince yourself that this identity is in fact true. Now, if you stare at this from part A of this result, I know, although that was proved for two sequences, by induction it is actually true for any finite. If you add up any finite number of sequences, the limit is going to be the sum of the individual limits, right? So I have broken up the sequence x and yn into 4 sequences. One of them is a trivial sequence, which is a constant xy. The second is in fact the product of xn minus x and yn minus y. The third is x times yn minus y, and the fourth is y into xn minus x. Now, one thing to note, right, this is something that is fairly obvious from the definition of the limit, but again, something that one should just know is that to say that xn tends to x is equivalent to saying that xn minus x tends to 0. Okay, to say that xn converges and has a limit x is equivalent to saying that the sequence xn minus x converges and has a limit 0. Okay, now if you see it like that, well, this term number 3 clearly goes to 0 because it's just a scalar times yn minus y. From part C, a combination of part C and the fact that yn minus y goes to 0 implies that the third term goes to 0. The fourth term goes to 0. Similarly, if I can argue that this second term also goes to 0, then I'm done, because xn yn is equal to a constant plus 3 other sequences, each of which go to 0, which implies that xn yn tends to xy, right? So it suffices to show that if you look at xn minus x into yn minus y, this thing goes to 0, right? And how am I going to do this? Well, I'm going to, again, earlier we additively decomposed the error threshold epsilon into two pieces, right? Epsilon by 2, epsilon by 2. Here I'm going to multiplicatively decompose the error threshold into two pieces, each of them being square root epsilon. Okay, so we know that there exists, let's say, an n1 such that the absolute value of xn minus x in fact is less than square root epsilon for all n greater than or equal to n1. This follows from the fact that xn converges to x. Similarly, there exists an n2 such that yn minus y is in fact less than square root epsilon for all n greater than or equal to n2. Now I'm going to set, as before, n0 to be the max of n1 and n2, such that for all numbers greater than or equal to n0, both of these properties hold, right? So in this case, you can check that for n greater than or equal to n0, if I now look at xn minus x into yn minus y minus 0, right? That's just exactly this. I have to show that this absolute value is less than epsilon for all n greater than equal to n0, which is clearly true because in fact this is less than square root epsilon times square root epsilon, which is of course epsilon. Okay, so that in turn proves that the second piece basically tends to 0, and so yeah, and the first piece is just a constant, so therefore from here it follows that xn yn tends to xy. Okay, so this is really the proof of part 3. All that remains now to prove this theorem is to prove part D, which is, I'm going to remind you what the question was. The question was that for x not equal to 0, 1 by xn in fact tends to 1 by x. Okay, so yeah, maybe this is good. I can probably leave this as an exercise to you, and we can discuss this in the tutorial if need be. The only thing I want you to think about is that in this case, so this is an exercise, and you want to, again, you have to basically understand the error between 1 by xn and the claimed limit, which in this case is given to you. This, if you look at, it's going to be xn minus x upon x times xn. Okay, so one has to now deal with the fact that there is also an xn sitting in the denominator, and argue that the fact that the entries of xn get arbitrarily close to x, where x is not equal to 0, implies that this entire thing also becomes arbitrarily close to 0. In other words, for every epsilon that is positive, I can come up with an n naught such that this fellow is less than epsilon. Okay, so yeah, give this some thought and in fact convince yourself that this is in fact true. So I'd like you to actually write down the proof for this piece on your own. Right? So let me move on. Now, so this was our first result. It's basically like we are trying to massage together some consequences of the definition of the limit. So the next property is in fact yet another trivial consequence of the definition itself, but it's remarkably useful. And this is called the sandwich or the squeeze property. Okay, what does it mean? So suppose that xn is less than or equal to yn, which is less than or equal to zn for all n, and you have that xn tends to x and zn tends to x. Then in fact you will also have that yn tends to x. Okay, so the idea, as the name suggests, if you can sandwich or squeeze yn between two sequences, so the sequence yn is upper bounded by the sequence zn, lower bounded by the sequence xn, and if you can construct these bounds in such a way that xn and zn both converge to the same limit, then in fact the sandwiched sequence yn also converges to the same limit x. Okay, so this is a very powerful way of proving limits of sequences. Again, the proof is fairly straightforward, so I'm actually going to still leave the proof of this as an exercise to you. But I hope the statement itself is fairly intuitive already, right? And now I'm going to use this to prove, well, a bunch more of results. So this lemma says, there are 4 parts to this lemma. For p greater than 0, 1 by n raised to p in fact tends to 0. Similarly, for a having an absolute value less than 1, a raised to n tends to 0. Part C says n raised to 1 by n tends to 1. And part D says a raised to 1 by n tends to 1 for a greater than 0. So remember, the fact that the nth root of any positive number exists is something that we have already established. Okay, so these objects n raised to 1 by n and a raised to n by n are perfectly well defined because of our development from chapter 1. Alright, so now let's go about doing this. So again, a and b are actually fairly trivial. So I'm going to lay out a bunch of these exercises to you. So your goal when you're watching this video basically has to be to internalize the statement of the definition of convergence of a limit and quickly be able to prove many of these properties and examples based on that definition. So A and B again is an exercise. I will, however, prove C, which is this is again a property that you've probably used as part of your calculus toolbook. That is, if you look at n raised to 1 by n, that sequence actually converges and has a limit of 1. Okay, so how do you go about proving this? So for this, I'm going to define this new sequence xn, which is n raised to 1 by n minus 1, right? So what I do need to show is that xn tends to 0. If I have shown that xn tends to 0, then clearly I have proved the statement of the lemma. Okay, so let us look at how one would go about doing this. The first thing to note is that xn is greater than or equal to 0. Okay, for any natural number, convince yourself that n raised to 1 by n is always going to be greater than or equal to 1. So the fact that that is greater than or equal to 1 implies that xn must necessarily be greater than or equal to 0, right? Another thing to note is that if you look at 1 plus xn, 1 plus xn is of course n raised to 1 by n. 1 plus xn raised to n is in fact n. So xn as defined has the property that 1 plus xn raised to n is equal to n. Okay. Now what I'm going to use here is the fact that 1 plus xn raised to n has a binomial expansion, right? We have all studied this, and given that each of the pieces in that summation is positive, it follows that, or at least non-negative, it follows that if I restrict myself to any one element or one term out of the binomial expansion of 1 plus xn raised to n, I will in fact get a lower bound on the right hand side, right? So I should therefore be able to conclude that if you look at the term corresponding to xn square in the binomial summation, remember the factor on that term is going to be n choose 2, which is n into n minus 1 by 2. So this is one term, specifically it's the second term or the third term, depending on how you count, of the binomial expansion. This is clearly less than or equal to n, right? From where I in fact argue that xn is less than or equal to square root of 2 by n minus 1. Okay, now in particular this is of course only true for n greater than 1, but that's fine, right? I mean, for n is equal to 1, this inequality, I don't need the inequality for n equals 1. Okay, so therefore for n greater than 1, I have that 0 is less than or equal to xn, which is less than or equal to this upper bound, square root of. Okay, and this you can check is actually also a sequence that tends to 0. So what we have done is basically managed to sandwich the sequence xn between 0 and an upper bound which also tends to 0. And so therefore, by the sandwich property, it follows that xn also tends to 0. Now one thing to note in the sandwich property is that even though the way I have written it, I have said that xn less than equal to yn less than zn for all n, you can convince yourself quite easily that I don't need this to be true for all n. If this is true for all n greater than a certain number, that's fine, right? So I don't need the sandwiching to hold for all n. It's sufficient if the sandwiching holds beyond a certain point. Which in this particular case, the sandwiching holds for all n greater than 1, which is fine. Okay, so this is how I argue that n raised to 1 by n in fact tends to 0. All that remains now is to show part D of this lemma. So I'm going to again remind you what that is. What we want to do is prove that a raised to 1 by n tends to 1 for all a greater than 0. Okay, so this is in fact a trivial consequence of part C, so it will be quite easy to prove. So to show this, first I point out that this is trivial for a equals 1. Yeah, this is just an observation I'm starting to make. The proof, in fact, I don't need to, for the proof it turns out I don't need to make this case separate. For a greater than or equal to 1, a raised to 1 by n is in fact less than or equal to n raised to 1 by n for all n greater than a. Okay, so my claim is that suppose a is greater than or equal to 1, the nth root of a is in fact going to be less than or equal to the nth root of n for all n that is larger than a. Okay, so what this means is that if you look at the special case where a is greater than or equal to 1, again let me reiterate that for a greater than or equal to 1, then in fact I will have this sandwiching hold. The nth root of a, you can convince yourself, is still going to be greater than or equal to 1, but it's also upper bounded by n raised to 1 by n. Okay, this is true for all n greater than a. So therefore, by sandwich property, we can argue that a raised to 1 by n goes to 1, right? Because the right hand side goes to 1, the left hand side is trivially 1, and so therefore a raised to 1 by n goes to 1, right? And the fourth, the last case here, which is the case where a is less than 1. If a is less than 1, then the argument again follows from part 2, because for a less than 1, 1 by a is going to be greater than 1, right? And the nth root of 1 by a therefore in fact tends to 1 from part B, or let's say this. So this is just a trivial case. This is case 1 really, and this is case 2, right? So this is true from case 1. All right, so from here it actually, we are almost done, because after all 1 by a raised to 1 by n is actually just the reciprocal of the nth root of a, okay, which implies again from our previous results that a raised to 1 by n tends to 1. Why is this part itself true? Well, this part is true based on the result that we are proving as part of this time's homework, of the homework corresponding to week 2, I believe, right? So 1 by a raised to 1 by n is in fact 1 raised to 1 by n divided by a raised to 1 by n. So this is something that we have already shown, or at least will show in the upcoming tutorial. Okay, so that in turn completes the proof, and that we can argue that for all a positive, a raised to 1 by n tends to 1. Okay, so these are again a bunch of examples which are consequences of the definition of the limit. I'm going to conclude this video with one last point, which is, I'm also going to introduce the definition of what it means for a sequence to tend to infinity. Okay, so given a sequence xn, we say xn tends to infinity if for all m greater than 0 there exists an n0 in n such that xn is greater than m for all n greater than equal to n0, right? So we intuitively, when I say that a sequence tends to infinity, what I'm saying is that the entries of the sequence are growing unboundedly, right? And this is how I would go about formalizing this, because by this definition, for any positive threshold you pick, you can pick m to be a million, a billion, a trillion, whatever number you pick, there exists a certain point such that the entries of the sequence beyond that point will exceed your threshold m, right? And since this is true for every large m, it's reasonable to say that xn tends to infinity. Okay, now one thing to note is, before I say that, I'll give you the other definition of what it means for a sequence to tend to minus infinity. So that's trivial. A sequence tends to minus infinity if the entries of the sequence kind of decay unboundedly, right? So they become progressively smaller and smaller and smaller and smaller, right? So we say that xn tends to minus infinity if and only if the sequence minus xn tends to infinity. Okay, since I've already defined what it means for a sequence to tend to infinity, I'm just going to invoke that to define what it means for a sequence to tend to minus infinity. Now, one thing I should note here, and this is very important so far as language is concerned, the word converge is reserved for sequences that actually tend to a real number. So if you remember, so far note that I have not used the word converge when I'm talking about these definitions of what it means for a sequence to tend to plus or minus infinity. Okay, so the word converge is reserved for those cases where the limit of the sequence is real, right? If you look at, remember the definition that we started this lecture with, we said a sequence converges if there exists a real number x such that the entries of the sequence become arbitrarily close to x, right? So this is important to note that the word converge or the term converge is reserved for the cases where the sequence actually converges to some real number. Okay, so in that language, sequences that tend to infinity and sequences that tend to infinity are also divergent sequences, right? So these are sequences that tend to plus or minus infinity are divergent sequences, just that they are special divergent sequences, right? In that they either grow without bound or decay without bound, right? Or decrease without bound. Okay, so this is an important point to keep in mind. So quick trivial example, if you look at something like square root n plus 7, right? It is easy to show that in fact xn tends to infinity, right? I repeat, in this case you're not allowed to say xn converges to infinity. That makes no sense. Convergence is always reserved for cases where the limit in question is a real number. Okay, so this is an example of a divergent sequence that tends to plus infinity. Okay, another example, suppose I say that xn is equal to n square plus 3 upon n plus 1. The claim is that this also tends to infinity, right? So yeah, let me just maybe quickly run you through the argument for this. Now, how do you show that something tends to infinity? You have to show that the entries are becoming unboundedly large, right? For every threshold m, beyond a certain point, the entries of the sequence become larger than m. So one way to do that is to argue that a lower bound on the sequence becomes larger than m for all n greater than n naught, right? So typically it suffices, yeah, you can go back to the definition and convince yourself that it suffices to show that a lower bound on the sequence tends to infinity. That implies that the sequence tends to infinity. Okay, so one way I could do this is, you assume, given some m which is positive, I look at xn, which is n square plus 3 upon n plus 1, and I'm going to lower bound this. The way I lower bound the numerator is of course by killing the plus 3. I'm just going to take n square. Now the way I can lower bound the fraction is by again upper bounding the denominator. I can upper bound n plus 1 by something like 2n, right? So which is therefore n by 2, and this is in fact larger than m for all n which is greater than 2m. Okay, so I can just basically set n naught to be, let's say, 1 plus the ceiling of 2m. Okay, so that's it. So this in fact is enough to show that this sequence xn in fact tends to infinity. And in conclusion, one final note I would like to make is that many of the theorems that we proved for sums and products and ratios of convergent sequences, they also apply to sequences that actually tend to plus minus infinity. Many results we showed for sums, products, ratios of convergent sequences also hold for sequences tending to plus minus infinity. Right? For example, if one sequence tends to 3 and another sequence, let's say xn tends to 3 and yn tends to plus infinity, then in fact xn plus yn tends to 3 plus infinity, which by definition is infinity. That's an example of where sums work fine. Similarly, in some cases, products work fine. So if xn tends to 3 and yn tends to plus infinity, then indeed xn yn tends to 3 times infinity, which is infinity. Similarly, if xn tends to minus 3, yn tends to infinity, then xn yn tends to minus infinity. So we've already talked about how rules of addition and subtraction, multiplication and division apply to the symbols plus, minus, infinity. Subject to those interpretations, some of these results actually can be easily extended to this. A trivial example of that is actually already here on this page. If you look at the example square root n plus 7, the xn is the sum of two sequences. The first term, the one involving square root n, trivially tends to infinity. The second term is a constant, so it just tends to 7. And in this case, indeed, the sum of those two the sequences will have a limit which is infinity. Okay, so that essentially brings us to the end of this video. If you think about it, the takeaway is simply that we defined what it means for a sequence to converge. We also defined what it means for a divergent sequence to either tend to plus infinity or minus infinity, right? These are just special cases of divergent sequences. And we did a whole bunch of examples and results which are straightforward consequences of the definition of the limit. Okay, so starting the next video, we will start talking about bounded sequences, monotone sequences, and Cauchy sequences.